Good morning. Welcome to the EasyPower Tuesday Refresher. My name is Jim Chastain, and we just wanted to welcome you all to contribute to the discussion by submitting questions or comments during the session. Today we're exploring the specific topic of setting up variable frequency drives in EasyPower, and we usually start this half-hour session with a poll question. So if you would all help the discussion along by contributing, I would appreciate the feedback. So we actually have 3 questions today, and they all have to do with your experience or your usage of VFD designs and your projects. So the first one is essentially, how often do you have VFDs? And just based upon people signing up for this presentation, I'm thinking there's going to be a fair number of people that are experienced in this area. Again, appreciate the feedback. It helps kind of direct the conversation as we get into the session, and it's a chance for you to help steer not only this discussion but future material. So here's, I'm going to close this block and show how things reported. And then the next question is, what's the most often, or what size is most often used, at least in your studies? And this is the one I really don't have a good feel of what to expect, and so I'm anxious to kind of see where the numbers fall into segments on this one. Again, thank you very much for participating, and we're going to close this out and kind of share this information. So it looks like it's usually the mid to small size that we're most experienced with. And then another topic that I'm really curious about is how often the feature regeneration is utilized in the designs. So leave this open for about 5 more seconds. And we do appreciate everyone for attending and participating. And so it looks like only 10% of the audience really utilizes regeneration a lot, and I appreciate that feedback very much. In fact, if you wouldn't mind a personal story, whenever I think of, or the topic of regeneration comes up, it brings to mind a very vivid personal example. Back when I was in school, I was privileged to work as an electronics technician at the Bevatron, which is located at the Lawrence Berkeley lab. And the Bevatron was actually a large circular particle accelerator used to produce the first antiprotons, among other discoveries. And it was powered by these large magnets that were used to bend the particle beam in a circle as the particles were bunched and accelerated. Well, in those days, the best way to produce high amperage DC was electromechanical. Since this was a government project, a motor generator that was actually repurposed from a World War II warship was used to power the magnets. Well, the system accelerated 10 beam pulses per minute. So to prevent a lot of wasted energy, the collapsing magnetic field reversed energy flow back through the motor generator to put the energy back into the local grid at the end of each pulse. Well, once or twice a month, the system might experience a fault which caused the generator output to be crowbarred, and in fact the currents were so high they had to use a section of a railroad rail to short the terminals, and at those times it would be obvious how effective the regeneration design actually performed. I worked swing shift, and if you were outside when one of these faults occurred, besides hearing the groan inside the building as the motor generator wound down, there was a perceptible dimming of the lights of Berkeley as the grid had to replace the missing energy, and it left a very vivid impression on me at the time. So I digress. Today's agenda is VFDs, and we're going to talk a little bit about the motor controls, a little bit about the pros and cons, and then how some of these parameters relate to the way the EasyPower models a VFD. Basic VFD has three primary sections for the most part. There's a rectification stage, the DC filtering stage, and then the motor switching stage, which generates the drive for the motor itself. And actually, these first were evolving in the early 80s, and the fact that higher current, higher voltage semiconductors were becoming available at that time made this type of motor control much more practical. At the time, the only way to have really accurate motor control was to use a DC motor because the controls were simpler to design. So as we get into the generation of a pulse width, primarily there are 5 or 6 different topologies that can be used for variable frequency drive designs. I think the most common is pulse width modulated, and the primary methodology for determining how wide the pulse will be. So what the motor will see is a series of pulses with different widths on the positive and negative side of the swing. And the way they generate frequently these pulses is by overlaying a sine wave with a sawtooth wave being the driver of the actual rail-to-rail voltage, which has been rectified, and the sine wave where it intersects the sawtooth determines the width of the positive and the negative pulse, as it were. So you can see on the bottom layer that we have wider positive pulses, or positive going pulses, and on the negative side of the sine wave, we see more width on the bottom of the pulse width modulation chain. Now, this frequency, the sine wave, is the frequency that's actually going to drive the motor. The switching frequency, that of the sawtooth, is what the switching elements are going to be running at, and these all have a part to play in terms of the impact on our system. The variable part is actually the control then of the sine wave, and this can vary between something less than 60 cycles to something more than 60 cycles, and frequently the switching controls will be several hundred hertz, if not kilohertz. I've seen designs where you have 1,000 hertz for the switching frequency, and some that go as high as 10,000 cycles and above for the switching frequency. So anyway, the point that can be seen, though, even from these kind of artist perception, because these are not accurate waveforms, there's a couple things that kind of fall off from this discussion. First of all, we have very sharp rise times during the switching cycle, that the energy that's delivered to the motor is actually the average integral under the sine, or the average integral under the pulse, that will approximate a sine wave, and that's how the motors are controlled. And so we're left with a couple different trade-offs when we start talking about VFDs. First of all, on the pro side, they do in fact reduce the amount of energy consumed in a motor, especially when it's running at something less than full speed. And it does allow us to have much more finite precision in controlling the speed of the motor and regulating that speed with a little bit of feedback loop. And it also improves the power factor in terms of specifically just the offset angle between the voltage and the current if you disregard the rise time issues. Now on the negative side, well, and then regeneration, there's a potential for recouping the kinetic energy of the motor if we have regeneration to push energy back to the line side of the controller. Very frequently, the control systems require heat removal because the switching frequency may be much higher, and the elements that have to endure that energy flow frequently have to have airflow over them to remove that extra heat. And then, as we could see from the waveform, there is going to be a fairly high concentration of harmonic generation because of the rise times involved, and some thought needs to be given to the effect of those harmonics on our system, whether it's in terms of filtering within the VFD itself or filtering in the system based upon the effect of these harmonics or the way that they're getting out of the controller. So all that in mind, let's kind of jump into EasyPower and see where this is going to take us. So what I have set up here is a one-line diagram that has several different motors that I've converted to VFDs. And the point I want to make is that this modeling technique has applications in several different parts of the system. First of all, let me just kind of start with adding a motor, and we'll talk about the basic elements of a controller. So anytime we add a motor to the system such as this, and we go to characterize it by opening the dialog box, it opens up a typical motor data dialog, and it's this checkbox here that indicates the difference between a standard motor and a motor that's going to have a VFD icon associated with it. Nothing really changes in terms of the way that we enter data. We're still going to talk about the horsepower that's being used, and as we go through the steps of setting up the motor, we will see that the X over R calculation has to be made, that the motor starting ratio needs to be adjusted, and this is probably where we'll see the biggest difference between the VFD and the standard motor. But then also, by default, when we go to the harmonics tab, where a standard motor is set up as a linear load, the VFD is going to be set up as a harmonic load. Now, when it comes to arc flash and short circuit analysis, this doesn't make a difference. But if we're talking about power flow and harmonics, then we need to pay a little bit more attention to this. So let's kind of walk back through this. You'll notice as I change between standard motor and adjustable frequency drive, there is a change in the kVA calculations. Just as a review, when I enter in the horsepower, kVA is generated, and with that is what's used to calculate by inference the full load current. If we use the calculate button, it will take this horsepower, and if this size motor is in the NEC schedule tables, then it'll reflect that FLA value here, and that will be used to calculate the kVA. Whereas if I leave this box blank, then the kVA is calculated from the size of the motor and the efficiency factors that we've already included. So if I indicate this as a VFD, you'll notice that the kVA has been changed. Likewise, the X over R is going to change in that respect, and it may or may not be significant in terms of the overall system design, but it will have something to do with the momentary current. And then I want to point out, while not all VFD controllers have the ability to be a regenerative system, there are some applications where regeneration is an important part of the design, and when that is the case, you want to make sure that you include the designation that it's a regenerative drive, because in fact, while it doesn't change the X over R, it will change the amount of feedback that we get from the current. When we're talking non-regenerative, there's actually no feedback at all from the motor, from the VFD during a fault. Okay. The next place we're going to, so this is how you set up a VFD as a standalone motor. There's also the potential for setting up a VFD as part of a motor control center, and that's very much very similar to what we just went through. As we go into the motor itself, under the description of the load, the choices that were permitted range from a standard motor to a standard load, VFDs, subpanels, motors with TCCs, VFDs with TCCs, and so when this is a VFD motor, we can choose non-regeneration or VFD with a TCC, and at that point, as we tab across, we'll be entering the same data that we would on a motor, and then the parameters as far as what's required to do the calculations for short circuit and arc flash are basically very similar to what we set up as a standalone motor. If we're going to do an outboard VFD, similar to what I've done here, let's take off this extra one that I threw in there. If we're going to do an outboard VFD, then we can either represent the motor as we just did and set up as we just did, and where it's connected to the into the buswork or the MCC, we will describe it as a sub MCC rather than some sort of an onboard load. At that point, it takes all the information, and we designate which cable we're going to. At that point, we utilize the data icon here for the protective device, and as we set up the breaker designations for this particular device, again, these will be set up just as we would a standalone breaker or a separate breaker, except this will describe one that's inside the MCC. And that's what will be used to plot the characteristic curves. Now, you'll notice the rest of the line, the conduit, the cable size, insulation, and the like, is grayed out, and that's because as we designate which cable that we've connected to, since it exists on the one line, that information is brought into the MCC. Okay, there's one more point and one more. Yeah, let's just do it this way. I'm going to delete this particular motor. I don't have to delete anything. I'm just going to start. I'm just going to deactivate it. So let's say instead of a VFD drive that was associated directly with the motor, I actually have a remote AFD or VFD controller and then some length of cable to the motor itself. How I would represent that is to utilize the AFD controller, and let's kind of come back here and dig it off of my equipment palette. All right, so also in the tool equipment palette, there's an adjustable frequency drive icon, which allows me to do the following. So as I kind of indicated, we have a system where I have an MCC, which has an outboard VFD controller, and then some length of cable now to the motor itself, where they're not necessarily side by side, in which case I would construct it thusly. And this will depend in a large part upon how my system's constructed. Let's say for now it's a 480 volt motor, and at this point I represent it as a standard motor. So let's say this is a 50 horsepower standard, and nothing too special about this motor itself, except now when we get back to the AFD description, we open up the dialog box, and this is where we control the ratings and the VFD itself. So let's say this was, again, a 50 horsepower VFD. We calculate the X over R. Here, the IGBT is the only side of the output that's actually been modeled. Thyristor can be indicated, but it doesn't affect the calculation. As I mentioned earlier, if for some reason we have a different output frequency than 60 cycles, this is where it would be. And so this may be higher or lower than 60 cycles. Let's say in this case it's 40 hertz. The multiplier of full load current during a fault by default is 1.5. If we have something different on our data sheets, that's where we would enter it here. Most often the fault time in a semiconductor protected device is specified somewhere in the neighborhood of 0.2 seconds. Again, this is part of the data sheet, and this element is instrumental in how the arc flash is calculated on those buses downstream of the device. And then finally, and so if our data sheet has anything different than what's being used here as standard, obviously we want to utilize that. And then where there's regeneration, we'd indicate that here. And then finally, again, when we go to harmonics, because this is an AFD, and this is true even in a standalone motor, being defined as a harmonic load, if we don't have the specific harmonic contributions from the data sheet, we can use, in this case I'm going to select an industrial library load, and we can describe the type of controller that we're using or the type of harmonic generation that's being used. And these are approximate numbers, but they give us the loading of, or based upon the PWM capacity, how much the harmonic generation contributes. So you'll notice if we pick 65% and import it, we have harmonic content as high as 39% in the lower 5th, 7th, 11th harmonics, whereas if we pick a less or more lightly loaded PWM profile and import it, we end up with a much higher harmonic content at the lower harmonics. So again, this gives you an order of magnitude if you're going to be looking at the harmonic contribution from a particular load, and these same values are available whether we do it in the standalone AFD setup or in the individual motor setup. So here we got a 65% load, and if we look at something less, we notice that it goes quite a bit higher. All right, so that's, I don't think I missed anything there as far as the basic setup. We can go in and look at the short circuit calculations. Let's see what I need to tell it how big the cable is down here. So let's just take a copy of this and put it down here. Not today. So now when I go to my short circuit focus and fault the buses, I guess what I'm expecting to see is a significant difference in my contributions at each of the buses. And down here you'll see we're showing nothing, so let's understand what's going on there. If I fault this downstream bus and look for my arc flash energy, it's going to tell me there's no valid device. Let's kind of go back and see how that can be. If I go into database edit, and what I expect to see is it's because it's in regenerative. If it was non-regenerative, let's see how that affects things. Nope, I was wrong. Regenerative should make a difference as far as the contribution up here. So let's look at current. All right, so in fact, this is kind of a good point. What we're showing here is the fault current return from this motor, and the fact that we're in a non-regen mode, nothing's returned back to this particular bus. If I go into the setup and make this regenerative and fault that bus again, you can see now we have 180 amps coming back from the load during the regeneration cycle. Now, just while I'm here, because I'm curious, if we look at our short circuit options, arc flash, including main, it's not clear to me why I'm not getting a, because we do have 90 amps. I'd expect to be able to produce an arc flash label downstream. So I'll have to get back to you on that one, why I'm not seeing one down here. All right, so what have we covered? We've talked about the different types of pulse width modulation. We've talked about how to set up EasyPower for pulse width modulated or variable frequency drives that are outboarded, that are standalone, and that are remote from the motor itself, where you have some cable run between the motor and the VFD controller. There's a small amount of difference in the arc flash calculations, and as I say, I'll have to get back to you on why I'm not seeing an arc flash energy downstream of my controller, given my AFD fault time protection. And finally, we just touched on the fact that there's a lot of harmonic content anytime you use a VFD drive, and the larger the motor and the lower the loading on that motor, the larger that contribution, and that takes us into the world of harmonic analysis, and so we'll touch on that when we get to that topic. All right, I think that's pretty much what I wanted to cover today. Let's see if there's anything left on my agenda. Thank you everyone for attending. I will be checking to see if we have questions, and I will respond to everyone with specifically what looks like I misset up as far as my arc flash calculations. Thank you for attending. Certainly anyone with any tool owner with current maintenance has continual access to tech support at easypower.com for questions about AFDs or any other topic in the EasyPower sphere of influence.